Oh, so today, me and my two partners, Sam and Henry, they'll be in the video later, we are going to be determining the normal and shear force and moment force on this beam at point C, pin at point A, and roller at point B. To start off, we have a trapezoidal load distribution. To determine at what direction it's at and distance, we're going to cut it up into two pieces. So we're going to have a rectangle piece and a triangle piece. I'm going to call this area 1 and area 2. So this spot right here, 200 Newton divided by meters. And then this spot up here, not the full thing, can be 200 meters. So now we have to determine the areas in both of these. So for area 1 of a triangle, it's 1/2 times base times height. The length, the full length, right here, is 6 meters. So 1/2, area 1, again, top 1, times base, 6, times height, which is 200 right here, for area 1, equals 600 meters. Area 2 is a triangle, square. So for area, it's just length times height, or length times width. That's gonna be 600 times 200 again, which equals 1200 Newton divided by meters. Now we gotta determine individually where at points the load will be acting on. For a rectangle, distributed load, quickly draw this for you. To find D at where the load is at, it is going to be length divided by 2. So you take the length, divide that by 2, that is where the load is going to be acting on for the rectangle piece. For the triangular piece that we cut up, again, I'll quickly draw it for you. Nearly the same thing, but it is L over 3. So area 1, which is the triangle, we're going to use this formula, D, which is the distance at which it's at, and it's going to be the length, the full length, 6 divided by 3, which is just 2 meters from point B though. Same thing for area 2, distance L over 2 this time, it's going to be 3 meters again from point B. And then to find the total, we're going to set up, first we have to get the total area, which is just A1 plus A2, which are these values, equals 1800. And then now we know the distance for these, but we don't know the distance for area total yet. This is where this equation comes in at. 600 times 2 plus 1200 times 3 equals 1800 D. And that's where this D is for this. Now we solve for D, will just be 2.67 meters from point B.
Now we draw the free body diagram of the part that we had, and we can see from here, from A to this point right here is 10/3. So we'll just label this as 10/3 because this whole thing, 6 minus 2.67 is 10/3. And then now we take the moment about A and we use the clockwise as positive. The force times the distance from A minus by times 6 meters from from A equals 0 to find By. And now we can find the By equals 1,000 newtons. Step 2, we come over to the section diagram at C, and we're going to find shear, moment, and axial force. We know that 1800, same distance as up there. So we'll start off by finding the axial, labeled positive direction. Find that N equals 0 newtons. There's no force in the x direction. Find the shear force, Y, positive direction, Y, force, the Y, plus shear equals 0. To calculate, we know that By equals 1,000 newtons, so we can say that V equals 800 newtons. And now for the moment, we can find that the moment about B to find the moment right here. So we'll label it again. Positive direction. Shear times 3 plus the moment minus the force times 8/3 0. Distance. Then we get M equals 1800 times 8/3 minus B times 3. V is 800. So then now we can say the moment equals 2400 meters.
And now we're on our final step, and this is an optional step. We're just gonna check that we did all of our work correctly by solving for the other side of the beam. So we're gonna look at the left side of point C. So first off, what we need to do is we need to solve for the support reactions at A. And in order to do that, we're gonna have to take the moment around point B. That equals 0, which equals AY at a distance of 6. And then that would be in the negative direction, because counterclockwise is positive. And so then we would take plus 1800, and using our distance that we found in part 1, 2.67. Or that would be 8/3, I believe. And so we calculate this out, we get AY equal to 800 newtons. And so once we have our support reactions, we can take this and go over here, but forgetting one thing, we need to solve for the second support reaction, AX. So in order to do that, take some of the forces in the x direction equals 0. And I'm looking up here and I only see one thing in the x direction. It is AX. So therefore AX is equal to 0. So that is also why we did not draw AX over there, because it doesn't exist. And so in order to find the internal forces, this one is pretty simple. The only force on it is AY in this case. So what we're going to do, we're going to start off with, again, some forces in the x direction. We're going to be thorough. Forces in the x equals 0. And the only thing here is the normal force of C. So we get normal force of C is equal to 0. Next up, we're going to take some of the forces in the y direction. Y direction is equal to 0, which is equal to AY. And negative VC. AY minus VC. So if we remember from over here, AY is equal to 800 newtons. And so VC is equal to 800 newtons. Pretty simple. And then lastly, we're going to take our moment to find the moment around point C. Some of the moments 0 equals, we have, looks to be positive moment. Well, it's opposite of our previous one, so we're gonna assume that it's positive. We're just gonna have plus m, or just m, and then ay, which would be negative ay, and then that is 3 meters. And then solving this out, we get m is equal to 2,400 Newton meters. And there we have it. We have our VC, our moment around C, and then our normal force on C.
Thanks for watching.